Hi Bobcats. In this video we're going to take a look at a couple more examples of ice charts to show a couple of different problem-solving techniques using them. In this example with PCl5 in equilibrium with PCl3 plus Cl2, we're going to have an ice chart that gives us a quadratic equation that there's just no way around, and we're going to have to use the quadratic formula to solve it. This one will not fall into the pattern where both sides of the equation are a perfect square and we can just take the square root. So this one gets to be tedious in an algebra sense, trying to get through this particular problem. Okay, so if we're going to set up our ice chart, we will have PCl5 in equilibrium with PCl3 plus Cl2. Now, all of these species are gas. They all will appear in our K expression, and so we'll include them all in our ice chart. Initially, in this problem, we have PCl5 at a pressure of 1.66 atmospheres. Nothing is said about the other two gases, so they are zeros. To reach equilibrium, this reaction will have to go to the right. It can't go to the left. And so that means that the change in PCl5 will be minus X as some of the reactant reacts and turns into product. Every time we lose X worth of PCl5, we're going to gain X in both PCl3 and Cl2. So at equilibrium, we'll have 1.66 minus X, X, and X. If we look at our K expression, K will be equal to PCl3 times Cl2 all divided by PCl5 down there in the bottom. The number that we have for K is 0.497. The value that we have for both PCl3 and Cl2 is X. So X times X gives us X squared up top. And down in the bottom, we're going to have 1.66 minus X. Now, I'm going to multiply both sides of this equation by that denominator, 1.66 minus X. And that's going to give me 0.497 times 1.66 minus X is equal to X squared. Next, I'll distribute, and that's going to give me 0.825 minus 0.497x. That's just distributing the 0.497 times 1.66, and then the 0.497 times a negative x. And that's all equal to x squared. Now, this is an example of a quadratic formula. We have an x squared term, an x term, and a constant. In order to solve this using the quadratic formula, we need it in the form of ax squared plus bx plus c is equal to 0. So I'm going to, let's see, since I already have two of those terms on the left-hand side, I'll just move the last one over to the left-hand side as well. That'll give me negative x squared minus 0.497x plus 0.825 is equal to 0. And it's perfectly fine to leave it this way. I had a math teacher who, in something like this, would always want us to turn that negative x squared into just positive x. So I'm going to multiply every term in this equation by a minus 1 just to change all the signs. That'll give me x squared plus 0.497 minus 0.825 is equal to 0. And now I'm ready to plug that into the quadratic formula. Now, on a timed test, I would never give you something with a quadratic formula because it takes too long on the tedious algebra. So if you run into something like this on your sapling homework, what I'd strongly recommend you do is open a different tab in your browser and Google a quadratic formula calculator. The A term that it's asking about is the coefficient in front of the x squared, which in this case, since nothing is written, it's understood to be a 1. So A would be 1. B would be the, whoops, I forgot to write an x twice here when I rewrote that equation. The B term is the coefficient in front of the x, so the 0.497, and the C term is the constant. Remember to keep that negative sign with it, negative 0.825. So if you plug that into one of these quadratic formula calculators, it's going to return back two values. It's going to tell you that x is equal to 0.693 and x is equal to negative 1.19. We have both a positive root and a negative root. If you look at our ice chart, x appears on the equilibrium line as the pressure of PCl3 and Cl2, and pressure can't be a negative number, so this root is not a physical possibility. So the correct answer will be that x equals 0.693. But that's not exactly what we were asked to find. We were asked to find the equilibrium pressures of all three chemicals. Well, it turns out X is the pressure of two of them, right? If we look at our equilibrium line, the pressure of PCl3 is equal to the pressure of Cl2, which is equal to 0.693 atmospheres. And then the pressure of PCl5 will be 1.66 minus X, or 1.66 minus 0.693. So PCl5 will be equal to, 0.967. So those are the answers that we were asked to find. The pressures of PCl3, Cl2, and the pressure of PCl5. This next example gives us an equilibrium situation where not all of the chemicals that are present in the equation are going to appear in our equilibrium constant. We only put gases and aqueous solutions into our equilibrium constant expression. So for the reactant, which is a solid, the ammonium methiol, I'm not sure actually what you would call that. I probably should have looked that up before I started making this video. The NH4SH is a solid and will not appear in our equilibrium constant expression. So we will take our equation to set up our ice chart. NH4SH, solid, in equilibrium with NH3 plus H2S, where both of those products are gases. Now, because that reactant is a solid, I don't need to waste any time coming up with values for it because it's not going to appear in my equilibrium constant. Now, the problem tells us that a sample of solid NH4SH is placed in a closed vessel and decomposes until equilibrium is reached. So initially, we only have NH4SH. NH3 and H2S initially then must be 0. As this reaction reaches equilibrium, we are going to gain X in ammonia and X in H2S. So at equilibrium, each one of these will be equal to X. Now, if I set up my K expression, K is going to be equal to ammonia times H2S. The reactant you could think of as being a denominator of 1, and then we don't normally write denominators of 1. K has a value of 1.2 times 10 to the negative 4. Notice that K is a Kc, so that means that these concentrations will be in terms of molarity. And for ammonia, I have X, and for H2S, I have X, so that'll be equal to X squared. If I take the square root of both sides, over there on the left-hand side, I'm going to have 0.011 if I write it in regular notation and not scientific notation. And on the right-hand side, I'll have X. So since X is the concentrations, is numerically equal to the concentrations we're looking for, we know that ammonia's concentration is equal to the concentration of H2S, and both of those are equal to 0.011 molar. And again, I know that's molarity and not pressure, even though these are all gases, because we were given a Kc and not a Kp. Oops, that was not what I intended to do in writing that line. Let's try again. All right, there we go. Our objective for these last two videos was to use ICE tables to solve equilibrium problems. We saw several cases that can pop up. One of the common cases is that both sides are a perfect square. And when that happens, you just want to take the square root of both sides. We also saw a situation where there's no way around it. You've got to use the quadratic formula. You'll have to do that perhaps on your homework. The Sapling Learning homework platform is algorithmic, so different students get different numbers. So you might have to, you might not have to, but I won't ask you to do that on a test because the algebra takes so long when you do the quadratic formula by hand. And then in that last case, we had one that potentially could have led to using a quadratic formula, except that the reactant was a solid, and so it doesn't appear in our equilibrium constant expression. So you just always want to make sure that you're omitting pure liquids and pure solids from your K expression, and that usually simplifies your K expression down quite a bit and avoids the quadratic formula.